the electron correlation, I just thought I would again mention the severe facts that we talked about. One is that if you have two electrons in parallel spin in any two orbitals, they have a Coulomb interaction, but they also have an exchange interaction. If you have electrons which are anti-parallel, you only have Coulomb and not the exchange. So that is the genesis why there is a Hund's rule, because in addition to Coulomb and exchange, there are of course one electron energy. So if there are degenerate orbitals, one electron energies are exactly identical. So what only matters is the fact that the parallel spin has a Coulomb and exchange. Anti-parallel has only Coulomb. So that is what leads to the exchange stabilization. This was shown from the energy expression. If you recall that we wrote that the energy is always sum of the spin orbital energies for the one electron and the Coulomb and the exchange two electron integrals, which was chi I 1 by r1 to chi I chi j minus. So this, note that this is the form of the energy given a single determinant, average value, we wrote. Again, just to put you in this perspective, our Hamiltonian is sum of h of I plus 1 by r. So this is the standard form of the Hamiltonian. So all the one electron part is put in small. So it is not that is kinetic energy and that is potential energy. I am repeating again, because many people feel that is kinetic, that is potential. Potential also has a one electron part, which is electron nuclear attraction. So all one electron part is put here. Whatever is two electrons are put separately. So it is not that the H is only kinetic energy. It has kinetic energy plus electron nuclear attraction for atoms or molecules. If there is external field, which is also one electron part, everything goes in small h. If you have such a Hamiltonian, then the energy, which is an average value over this side, which contains n spin orbitals, chi 1 to chi n. So that essentially defines my determinant. I am not writing in the matrix for determinant form, but you can expand it into a determinant form by keeping each row as one spin orbital, column as coordinate, or vice versa. So, but that's an abbreviated form of writing. I just have to write the n spin orbitals. Then the energy average value of the Hamiltonian with respect to this determinant can be written in this form. So that's the first thing. Then you can see that when I have a Coulomb, chi I can be alpha, chi j can be alpha, or chi j can be beta, or chi I can be beta, alpha, beta, or beta, beta, beta. So all four possibilities are there. That is, whether chi I is alpha spin, or chi I is a beta spin, and chi j is alpha spin, or chi j is a beta spin, everything will survive. Because the spin integration is only between here and here. Note that these are Dirac notation. So again, those who are not familiar with this notation, let me write this explicit form as integral chi I star 1, this is the coordinate 1, integral chi j star 2, 1 by r1 to chi I 1, chi j 2, beta 1, beta 1, beta 2. So this is basically called the Dirac form of writing the integrals, which is sometimes called 1, 2, 1, 2 form. So as you can see, lexical order, if I write, it's a 1, 2, 1, 2 form. Quite clearly, the spin integration is trivial. Whatever is the spin of chi I here, the same spin occurs here. So that becomes 1. Here also the spin integration is trivial. So either alpha or beta spin, this term always will survive. Spin integration will not knock this off. On the other hand, if you look at this term, chi I is 1, and by this nomenclature, of course, this is 1, this is coordinate 2, this is coordinate 2. Now 1 will integrate with 1. So if chi I has alpha spin, chi j must have alpha spin. Otherwise it will become 0 because of spin orthogonality. So that means if I is alpha spin, j must be alpha spin. If I is a beta spin, j must be beta spin. So this integral survives only for parallel spins, either alpha alpha or beta beta. Whereas the first integral survives for either alpha beta or beta alpha. So that was essentially the point that we made, and that is a very important point. So this is why there is a Ohm's rule. This is why parallel spins are favored unless this term offsets. So of course, if this term offsets, then it's a completely different matter. So whenever I have a Ohm's rule, we assume that the energy levels are degenerate. So basically for the orbital energies, these terms are similar. So all that matters is the Coulomb and exchange term, and then parallel spin has a Coulomb as well as exchange. So that is the reason the parallel spins are favored. But in anti-parallel spin, the second term is missing. Because if I is alpha, j is beta, that will become 0. As I showed you, because of the spin integration. If I is alpha, j is beta, when I integrate on the coordinate of 1 of the spin, it will become 0. Alright? Alpha beta is 0, right? So that's overlap integral. So that will not survive. So that is the genesis of Ohm's rule, which is also same if in inorganic chemistry I told you of the complexes, depending on the gap. So if the gap is very large, they can make a anti-parallel spins. That means they are sacrificing exchange because the 1 electron energy is much lower. But if you bring these close, then you will see that slowly it will become parallel spins. Because this difference is not so much, then the parallel spins tend to may compensate that, and eventually in the case of strict degeneracy, the limit is Ohm's rule. There has to be parallel spin. So that is what it is. So let's say that I give you an example and how quickly you can write this. So let us say that I give you this integral. This is 1, this is 2. I want to write the energy expression in terms of these integrals after spin integration. What survives in terms of spatial integration. So it's very easy to do that. First, this kind of terms are called Coulomb. So if you do this spin integration in terms of space, it is called Jij. So where chi is phi I alpha, okay, and chi j can be anything, phi j alpha. This also can be beta, this also can be beta. So I and j are the spatial, so this is j. So in terms of spatial integral, this is called j, this is called k. This is a standard notation. So if I use this notation, what would be the energy for this? First, of course, the 1 electron part. So you will see if I do the spin integration, it's a W occupied. So this will have 2 times H11. Again, I am using a simple notation where HII is in terms of spatial orbitals, phi I, H phi I. Please note that I am not writing chi because spin is now integrated. Alright, so I am writing only in terms of spatial orbitals phi. So this has 2 special orbitals for this electron, this orbital, plus 2 H2 for this. Alright, so we have 4 1 electron terms, 2 of them are H11, 2 of them are H2. So it's very easy to understand this because then chi is basically phi 1 alpha, phi 1 beta, phi 2 alpha, phi 2 beta. So all the 4 chi's are there, so you can easily do this spin integral. Then you want to write the Coulomb and the exchange term. Now the formula is very simple. Every pair of electrons, whether parallel or antiparallel, I told you, contributes to the Coulomb. Only antiparallel contributes to the exchange. So now how do I write this? How many pairs of electrons are there? 6. Because there are 4 electrons, so 4C2 is 6. Out of the 6 electrons, 2 of them are in 1. So I will write this as J11. So now these 1-1s are special orbitals, J11. Then a pair is in orbital 2, so J22. Then there are 4 pairs between 1 and 2. So this will be written easily, you can see, as 4 J12. So which means connecting phi I, phi j, Coulomb interaction between I and j. And then we have to write, so there are 6 now, 1 plus 1 plus 4, which is what it should be. But for k, I have to pick up anti-parallel, parallel spins only. So how many parallel spins are there? 1, 1. So there are 2 pairs of parallel spin, right? So that is minus 2 times k12. Each of them has k12. So that's it over. So if I look at the determinant, I can immediately write down the energy. After spin integration. So these indices are now indices for space orbitals because spins are integrated. Okay, so it's very easy to write. So you give any determinant, I can just write down. It doesn't matter whether it's a singlet, doublet, whether it is spin adapted. It's just a determinant. I told you it cannot be spin adapted, but you can write down the energy. So it's a good practice problem to do that you can keep doing. So you can take, for example, a determinant like this, 1, 2. So energy would be now 2H11 plus H2. 3 of them. There's only one here. And there are 3 pairs of Coulomb. So one would be J11 plus 2 pairs of J12. One here, one there, one here, one there. How many parallel spins are there? Only one. Minus K1. It's very easy to write. For K, only pick up parallel spins. So here you can see there is only one parallel spin, both are alpha. Okay, so it's K12. If this was downspin, also it would be result would be identical because spins are anyway integrated. So it doesn't matter whether this would be alpha or this would be beta. Result will be identical as it should be. Right? So I think it's very easy to apply the spin integrated formula for this in a very simple way. And remember, the H is not just kinetic energy. Again, I repeat, it is the entire one electron energy. Okay, so as long as you understand that, after that it is very easy to write by inspection, simply by inspection, but this actually comes from this expression. So very important results. Every pair of electrons contributes to a J. However, only parallel pairs contributes to a K. That's all you have to remember. The J has contribution for all pairs, K has contribution only from parallel pair, and K comes with a negative sign. So that is also something you should remember. So for parallel pair you have J minus K, for antiparallel pair you have only J, and hence the genesis of the Hunsu. Okay. Alright, so now what we want to do is to see how can we go beyond Hartree form. Obviously, this is a very huge subject as I told you yesterday. So what we are going to do is only to show you how do you what are the ways to expand this. So just the broad outlines rather than any details. Before I do that, let me first write down the Hartree form. I did not write down the Hartree form equation. I don't want to write down even now. But I told you that if you vary the psi h psi, this quantity, energy, with respect to the chi's, then the optimum energy is going to be the Hartree form energy. Because this is greater than or equal to E naught, so the minimum is Hartree form. So that is the best single determinant. It so turns out that that equation is a one particle equation, of course. So you have H from here plus one effective potential, which let me call it V Hartree form. An effective potential chi epsilon I chi. So this is actually, you can see this is a one particle equation. This V Hartree, the trick is to get this V Hartree form. This V Hartree form is exactly what is known as a contribution of an average field, mean field. That's why it is called mean field approximation. What is interesting to note that this equation cannot be solved in one go because V Hartree form unfortunately depends on the chi's, all the set of chi's. So this equation has to be solved in an iterative manner because I don't know the chi's. So first I guess chi's, then I construct the V Hartree form, then solve the eigenvalue equation, reconstruct and keep doing till I reach a convergence when I can say that the field which defines V Hartree form is the same field which comes as an output of this. So this is why very often this is called self-consistent field theory. Many of you who read Hartree form is also known as a SCF. So the reason Hartree form is called SCF is because the procedure of convergence, and at the convergent point this is called, the field is self-consistent. So it is called SCF. So Hartree form is often called just SCF. Okay? So this is what the Hartree form equation is. V-Hartree-Fock has a little complicated structure I am not writing, but this is basically an average of 1 by R12 over this chi-i's and chi-j's, a one particle average. So that is the reason Hartree-Fock includes, the V-Hartree-Fock essentially cannot be determined without knowing chi-i's. So only at the optimum point when Hartree-Fock is completely solved, I know the exact V-Hartree-Fock. So before that I don't know what is the Hartree-Fock potential, because I am solving it in an iterative manner, and that is the reason it is called SCF, self-consistent field theory. If we understand this, now I can look at a way to improve this. So one of the standard ways to improve this is by using perturbation theory. Now I don't want to give a long lecture on perturbation theory, but I hope I will just draw some of the essential equations. So in the perturbation theory, we normally have an H0 whose complete solutions are known. Alright? And then we want to construct the solution of H psi equal to E psi in orders of the residue, which is the V. So we write basically an H as H naught plus V, and then in various orders of V, the energies are written. The order comes because I start with a fictitious Hamiltonian, H of lambda is H naught plus lambda V. So lambda becomes my order parameter, and at the end of the solution I put lambda equal to 1, because I know lambda equal to 1 is my physical Hamiltonian, H naught plus V. But initially I extract the equation by doing the order parameter. So obviously, if I know the solution of H naught, the ground state solution of H naught, let me call this psi I0, let me call this EI0, psi I0. So the ground state solutions are all, for the zeroth order Hamiltonian, are written with a superscript 0. If it is ground state, I might as well use 0 here to denote that this is the lowest energy state for H naught. So E naught 0 is different from E naught. E naught is the lowest eigenvalue of the entire Hamiltonian. E naught 0 is the lowest eigenvalue of H naught, which is now my zeroth order Hamiltonian, whose entire solutions are known. So for H naught, I know all the solutions. So that is the reason I wrote this. I actually know all the solutions, including the ground state for H naught. So that is that is one of the important conditions before I start doing perturbation theory. That I must be able to separate out a part of the Hamiltonian, which in fact happens to be a dominant part of the Hamiltonian, whose entire solutions are known. Yes?
Yes, so this is a little backing off to Hartree-Fock. So any iterative self-consistency in a multidimensional problem is not guaranteed that you will find a point. So is there anything inbuilt in Hartree-Fock that guarantees finding?
No, even the convergence, right?
Convergence.
Yeah, absolutely. So, yeah, nothing can be built in, obviously. There are a lot of strategies that the people use for convergence, like Paddy approximation and so on, and we know in mathematics. So, various numerical methods are used. Most of the time, the problem converges because we start from a meaningful set of ties. That is very important. So if your guess is very bad, obviously like any iterative method, it will not converge. In most of the molecular cases, we have a good guess of what should be H